So hello everyone. As Ali said, my name is Erfan Rasouli, and I work in Western Cooling Efficiency Center. For those of you, this presentation whole is gonna cover some of the researchers' work that we are doing on some high temperature, high pressure stuff that is happening in our steel lab. It's a research facility. All right. Okay, so I guess some of those audience are coming from the WCC, but for those who are not familiar with WCC, it's one of the three entities with working with Energy Efficiency Institute, EI, and we are located across the street from where this event is happening. And so in WCC, we have significant expertise in climate appropriate cooling technologies, and we do have some expertise regarding the high temperature pressure compact heat exchanger design and experimentation. And we do, of course, laboratory testing. And so we have two lab environments, two labs. Actually, one is in WCC in West Village, which is shown, the schematic is shown on the left. It's an indoor air chamber, and most of those experiments and researchers regarding the HVAC equipment is happening here. But the research that I'm going to cover today is are those researchers that we are conducting in a steel lab. This lab is, if I'm looking at this map at the right, you see that where the WCC is located, and down in south of the campus, under the highway I-80, that's where we are. Here's this steel lab, and steel stands for Solar or Supercritical CO2 Thermal Energy Enhancement Lab. And so the PI of this facility is Professor Vinod Narayanan. I and also another engineer, Keaton, and two of the students are working on the researchers happening here. So at the moment, we have two ongoing researchers. Both of them are federally funded. One is from the CETO office and one is from the ARPA-E. And these projects started in 2019, and we have one more year to go. So we are almost concluding these two projects. We have several entities as our collaborators or subcontractors, but our main subcontractor is Carnegie Mellon University that worked with us on both of these projects. In fact, for the ARPA-E projects, the Carnegie Mellon is leading as a principal, but for the CETO, UC Davis leads the work. So giving you some background about the researchers happening at the steel lab, I can mention that in about 10 years ago, Department of Energy, Solar Energy Technology Office, CETO, they put together a roadmap to identify the technologies that works on the concentrated solar power, and in order to develop different variety of technologies that help to reduce the cost of CSP power plants. And in their very recent roadmap, which they call it Gen 3 CSP, they put the goal to reduce the cost down to 5 cents per kilowatt by 2030. And so this is, again, that is different. When we're talking about the solar, we usually think about the solar panels or PVs, but here we're talking about the thermal energy, where essentially we have a field of heliostats that are mirrors that are reflecting the sun to the central tower that collects the heat, thermal energy, and that heat goes down, can either go to the power block to produce electricity, or can be stored in thermal storage tank And then during the peak time, when sun is down, we can utilize that energy to produce electricity. So for these kind of cycle that we have these CSP and the power block, they kind of, we have three pathways. One is they call it liquid, gas, and solid particles. For the liquid, they're essentially looking at the varieties of these molten salts that goes to the tower. If it's gas, they're looking at to supercritical carbon dioxide. And if it's solid, they have different varieties of the ceramics or even a variety of sands that falls through kind of a process, falls as a curtain, and those particles picks up the heat and they come and go to the hot storage tank. And indirectly, they heat up the other fluid that goes to the power cycle. So the CSP itself is a high temperature, but when I'm talking about the high pressure comes from the power block section, where utilizing the.
Cut out for a second there, Erfan. Erfan, you there? Oh, no, Dan can't hear either. Bear with us, folks, technical difficulties. Oh, wait.
Oh,
I think his internet just dropped. We'll give him a second to rejoin. Erfan, are you back?
Ali, can you hear me?
There we go. Now you're back. Yeah, we lost you for a little bit.
Oh, okay. Sorry about that.
That's okay. And we lost your screen too. So if you wanted to reshare, I think maybe your internet cut out or something.
Oh, okay.
There we go.
So did you guys hear about when I was talking about this slide, or should I move?
Yeah, this slide was fine. You were talking about the three pathways. You were kind
Yeah,
of
exactly.
Yeah.
That for each of these pathways, that we need different heat exchangers to transfer the heat. If that's the media is molten salt, we need to transfer the heat from the molten salt to the media that goes to the power block. That's actually the CETO projects we are looking into. If we just look at the power block where it works with the supercritical carbon dioxide, we have another heat exchanger, we call it recuperator, that picks up the heat when it comes out of the turbomachinery turbine before going to the heat rejection section to preheat the flow in order to enhance the efficiency of the cycle. That's actually the ARPA-E project. So in ARPA-E projects, we are looking into the heat exchanger with heat exchange between CO2 to CO2. In CETO, we are looking for a heat exchanger that transfers heat from the molten salt to the CO2. Talking about the CO2, in next slide, I'm going, I hope I can move the, okay, here. Yeah, so looking at the left, that if for those of you that don't know about the supercritical form, that we have this liquid CO2, gas CO2, but there is a critical pressure and critical temperature that for the sake of CO2 is about 1000 psi and the temperature is about 88 Fahrenheit. When you meet both of those two, pressure and temperature, what's happening? The CO2, if it's gas or liquid, it moves to the new phase, which we call it supercritical. Supercritical it looks like a gaseous, but its density and its properties is more toward the liquid. So you can have kind of movability and fluidity of the gas, but you can benefit some of the properties that are close to the liquid. In left two pictures, I got it from a video on YouTube that you can search it and see there are some cool videos here. In top picture shows that CO2, you see kind of on the bottom section, it's a liquid CO2, and the temperature on the back is about 27 degrees C. But when the temperature, the pressure is already higher than critical pressure. But when the temperature goes beyond that critical point, then the kind of separation between liquid and gas, it's not there. Everything becomes like a most, I can say, kind of like a foggy shape. Now, in the middle plot, talking about the cycle efficiency, why they're not looking at the gas turbines or not the steam turbines, they're looking into these CO2 turbines. This plot kind of shows the cycle efficiency versus the turbine inlet temperature. The red line, again, shows the efficiencies that we can possibly catch when we have that cycle working with the supercritical CO2. You see that as the temperature goes higher and higher, the cycle efficiency goes higher. So even I'm at around 700 or 720 degrees C, which is about the temperature that CETO is looking into, the efficiencies of about 50% can be achieved. In terms of the properties of this CO2, also reduce the size of the turbo machinery. These pictures at the right kind of shows the comparison for about 300 megawatt. I took this picture from the Department of Energy website, comparing a 300 megawatt power block if it was steam turbine or CO2. So for the CO2 case, we are talking about a meter size, but in the steam, it was about 20 meters. So definitely there is a reduction in the size, and that in fact reduces the capital cost for the cycle. So here we have that high pressure. High temperature because of the sun, high pressure is because of the CO2. So recently I had a visit from the Southwest Research Institute, and over there, different entities in Department of Energy and some of these national labs are collaborating together to put together a facility that demonstrates this supercritical carbon dioxide power block in a small scale. It's not lab scale, but it's not also the industrial scale. So it's something middle, but it's still the kind of the technologies that can address the issues that they have here can be applied for the larger scales. So they are looking into about 10 megawatt net power block here. This picture at the left shows where the power block is gonna sit, and all of these equipment needed here. There is no solar field here. The picture that you see on the top is, I call it primary heat exchanger. They have essentially a gas-fired big chamber with a bunch of the tubes that preheat the CO2, or actually heated the CO2, and the heated CO2 goes to the power block to generate electricity. And I kind of bring your attention to the very right picture. That's actually a 1-to-1 scale of the shaft of the turbine, which has diameter about 20 centimeter. And this turbo machinery unit is capable to produce about 15 megawatt power. 5 megawatt is going to be used for the compressor, and 10 megawatt is net. So you can get a feeling that how small the turbo machinery would be if we have the supercritical CO2. And now let's just move on our projects. On the two projects that we have, I mentioned CETO is a heat exchanger that transfers the heat from the molten salt to the CO2. You can see kind of the design, the final, the current design that we have for this heat exchanger at the right, and the left shows the design that we have for transferring the heat between CO2 and CO2, but at different temperature and pressures. So both of these designs, there are different and that significant difference between these two, but what is common between these two designs is the core of the heat exchanger, where we are utilizing the micro channels or pin structures. So I can explain it a little better if we look at the left picture. Those plates that are sitting next to each other, blue, red, these are kind of showing the hot, cold next to each other. And these plates are filled with the pin, small pillars that are kind of, it's like a pin array, filled these plates and hold the plate together structurally, at the same time provides enhanced heat transfer by providing more heated surface area. So we needed, when we're talking about the project managers, so definitely they are interested to see that, are we moving toward their targets? Can our heat exchanger transfer the amount of the heat that they are looking into? What's the effectiveness of these heat exchangers? So at the first year, we had to make some assumptions. We had to make some thermofluidic model that predicted the result. So through the first and second year of the project, we had to try to validate those assumptions by doing some experimentations. Here in this picture, I'm showing several of the small test sections or pin arrays that we designed. Carnegie Mellon built it, sent it to us, and we ran experiment on this to quantify the heat transfer, to quantify the pressure drop, and use the experimental results to validate those assumptions that we made at the first place. So this slide shows, for example, the comparison. So if we have those pillars in the core, if we have taller, smaller, place them close to each other or sparse from each other, there is an effect that cause either higher pressure drop or lower pressure drop. These three plots are kind of comparing the pressure drop when, for example, in the very left plot, when we increase the height of the pins, the pressure drop goes down for the certain mass flow rate. And also for the other, I'm not going to the details for the other plots. Same thing is for the heat transfer when we are heating up the fluid. Okay, so also same thing is with the heat transfer rates in our units. We characterize all of them, and then we use these experimental data in our models. And also, another thing that I guess I missed to mention this, when we're talking about the high temperature, high pressure, so then the material that we are using, it's not gonna be very traditional like a stainless steel. So we are looking for the high, specifically designed, engineered materials, nickel alloy materials that are rated. They can have some strengths, creep strengths that can tolerate those harsh temperature and pressures. And if we deal with this material and make them traditionally through the machining, welding, those kind of things, since again, high temperature, high pressure, there are going to be very weak points that may result into the failure of the part. So one approach that, due to the advanced technologies for the additive manufacturing came, is that we can design a model and prevent from any joint, any welding, brazing, those kind of approaches, and make our heat exchanger all in one, in monolithic, one piece. We have just the ports that we just bring in and weld the pipes to bring the flow in, and out. But the rest is all in one piece to prevent all of those failure mechanisms that may happen when we have the plates welded next to each other. So Carnegie Mellon has that capability that they are making the parts for us. So when we design our parts, we send it to them, they print it, and it comes back to us for testing. So to prove one of those things that we talk about, the failure mechanism, that, hey, we are preventing any of these failure, we designed some samples that you are seeing the pictures left here, and intentionally remove some of those support structures, those pin arrays from the middle section. We put it in our chamber and heat it up, increase the pressure, and also try to validate our models to see that does this part fail at the location that we are seeing in our simulation. So we did those experiments and we got some failures that we were predicting. So we have better confidence about that. Those monolithic piece is gonna survive. Now, moving to the almost third year of both of these projects, we are becoming very close.
We just have a few more minutes left, Erfan. Just a couple more minutes.
This is actually on my last slide.
Oh, perfect. Okay.
Yeah, so we are almost in the third year, and then we are close to make the full-size heat exchangers that we promised for each of these projects. But before having the full size, we had to make some subscale size heat exchangers that the rating is lower, but it helped us to kind of debug our test loop or the fabrication problems. So these two, and this picture at the very left shows the design while it's 3D printed in the chamber. The middle picture shows the print when it's complete, and the right picture kind of shows the other view of these heat exchanger units. We kind of received one of these units in UC Davis and try to weld the fittings at the ports and then start our testing. So we are this is the kind of the very most up-to-date pictures and the very last steps that we are now. But soon and during the next year, we get almost a full-size heat exchanger here in UC Davis and characterize them and show them that microchannel technologies that we talked about, those micropillars, can transfer the amount of the heat that we predicted through our modeling efforts. This kind of wraps up my presentation, and I'm happy if you have any question, answer them.
Great. Thank you, Erfan. In the room or online, if you're online, feel free to chat your question or raise your hand. In the meantime, Josh, do you want to get your, you want use your computer?
Yeah.
All right, well, if you think of any questions, feel free to, we'll have some time at the end. And happy to have Erfan answer those then. Thanks again, Erfan. We'll switch over to Josh.
Sure.
All right, next up is Josh Morejohn. He's going to be talking to us about this district energy project that's going on here at UC Davis.
Is there a camera? Am I supposed to stand in a certain place?
There is a camera,
Okay.
but I think, let me see where, that looks great. Either side actually works. It kind of covers you wherever you are.
Okay, good. Great. Well, some of you have probably seen some of these slides before. This is basically an update. I gave an energy bite last year on our district energy system for UC Davis campus, and also the overall pathway to electrification and the part that district energy upgrades are playing in that pathway. So I want to give an update to that. I'm going to cover some of that ground again, because I know there's some new folks on here, and I'll give a little context to start with. I'm Josh Morejohn, Energy Manager in Facilities. This is kind of overview of my team on campus. We have a controls and energy engineering side, and then we also have an energy feedback and education side, which includes Jules the Cow, if you haven't heard of her. But some of you have probably heard about that side of it, our campus energy education dashboard and thermostat, a thermal feedback system. But then we also have a team that does energy engineering projects on campus. We manage the HVAC systems as well for the campus buildings. And then in my role, I do more campus initiatives for energy. And so one that I've been involved with for a long time now has been trying to convert the campus hot water or district energy system from steam to hot water. So a little overview of the campus for those who don't know, just to give you some context. It's a big campus, a lot of buildings, and about 8 million square feet of that 12 million square feet is connected to the district heating and district cooling systems. And we spend a lot of money on energy. In fact, my energy engineering team is funded by the energy savings that they get on campus. So they're saving this year. I think they're hitting $1.8 million of savings. That was about what we got last year too. And that's just savings off of our utility bill. So there's a lot of energy out there and a lot of opportunity, I think, for savings, and that's really just focused on building energy usage. But a lot of that is supplied by the district energy systems. So when people think about electrification, a lot of times the first place they go is PV, and starting to think about solar energy. We did think of that. That's one that we've got covered. We've got a 16 megawatt system, and it's south of campus. If you haven't seen it, it's pretty impressive. This is up close what it looks like. But what's surprising is, even though this is our dashboard showing the solar power production in the light green or yellow there, compared to campus electricity demand. And you can see in the summer, it's producing sometimes half of our demand, which is great. But when you look at the overall energy use of the year over the year, it's about 15% of our electricity, about 7% of our total energy. So even with a huge solar system like that, it's not going to get us to full electrification. We actually have another 30 megawatts off campus. So getting our electric supply fully renewable and carbon free is actually going to be the easiest part of electrification. The big challenge for us is the heating side. When you look at a campus and you think about electrification, beyond the solar energy part of it, there's this huge footprint of existing campus buildings and the energy that they use. Fortunately for us, we do have these district energy systems, and so I'm going to talk about the opportunity that you have when you have district energy. For the main campus, you see here, we actually have our large district energy system, but a lot of people don't know that there is a small district energy system at our primate center, which is 2 miles west of main campus, so even west of us here. And that one just got an upgrade, major upgrade. I'm not going to talk about that now just because we don't have time, but that'll be maybe next year, because it's coming online in the next month or so. We have a whole new central plant there. Really interesting systems. We were actually able to do some low temperature solar thermal there with some solar panels that were basically donated to UC system. And then heat pumps to step it up to a useful temperature. But we did a different approach out there because we didn't have the same opportunity that we had on the main campus, which is really about heat recovery. So there's 2 district energy systems on campus. Right now, they're completely independent of each other. We have a cooling system and a heating system. They're both really big. And on the cooling side, we have thermal energy storage. On the heating side, being steam, you can't do thermal energy storage, at least not very effectively. So that's one of the reasons that we want to go to a hot water system is the opportunity for storage. But the real opportunity is for heat recovery. So this chart shows our campus demand for heating and cooling being on the positive side and heating on the negative side in the red. And the heat recovery opportunity is illustrated here by the light blue section is showing the cooling that can be used for heat recovery to generate heating, which is the orange or light red section here. So all the orange is showing basically heating that can be done with heat recovered from the cooling side. So as the buildings are getting cooled, we're bringing that chilled water back from the buildings that cooled off the buildings and heated up the chilled water, and then that warmer chilled water can be used to run a heat pump or a heat recovery chiller and generate hot water at a useful temperature. And right now, those are completely independent. So all that heat that we're collecting from the buildings is getting thrown away through the cooling towers. A very low energy way to throw away heat, but it's also not being useful. So the opportunity is to be able to use that heating and cooling or use that heat recovered from the cooling system to do heating. And that would actually cover about 50 to 60% of our heat load for the campus. So it's amazing when you think about the fact that we can almost for free heat 60% of the campus throughout the year with this heat. And that's including daily storage. So the heating that goes on during the summer is oftentimes at night or in the mornings. As you know, with our climate here, we have these nice cool nights and mornings. Campus is running, buildings are running, lab buildings are 24/7. They're having to heat even in the summer at night and in the morning. So the opportunity is that we're collecting heat during the day when we're cooling in the summer, and we can use that heat at night or in the morning throughout the year. What we can't do is some of that heating in the winter when we don't have enough cooling to do all the heating, to meet the heating needs in the winter, to be in like January and December. But the opportunity with hot water, this is showing a little graphic our consultant AEI developed, just illustrating that kind of the potential when you have district energy, when you have low temperature hot water and chill water systems and thermal storage, just how many opportunities there are to get either low grade heat that can go into your cold storage. So you're able to heat chilled water with various sources and then use that heat in a heat recovery chiller or a heat pump. And places you can either use or generate heat as well. And so the big motivation to go to hot water is that this opens up the door to all kinds of different energy sources, whereas with steam, we're tied to natural gas. And with you guys heard about if you were here last week about the fossil-free plan and even just our carbon neutrality plan, the campus is tied right now to 40% of our carbon footprint is in our steam heating plant. So if we're going to get carbon neutral, we really got to get off steam. I'm not going to go into all of these. The consultant actually looked at a lot of opportunities for heat recovery. We have a wastewater treatment plant we could recover from. We have a lot of groundwater we could recover low-grade heat from. A lot of those systems are just not big enough to be at a very useful scale, but they could be additive and they could be something we use when we have a hot water system. But the big opportunity is really just like I said, heat recovery from our existing district energy system. It's basically a heat collection system. We can then use that heat if we have a hot water distribution system as well. So to do the life cycle planning or the analysis and decide exactly what kind of system we were going to do, we worked with a consultant for a couple of years and looked at a variety of systems. Just really quickly, this shows a life cycle cost over 60 years. Staying with the existing steam system, and it's by far the most expensive. This includes both the operating costs of gas and electricity, and then this is capital expenditures, which with an old system like we have, it's going to have to be renewed over the next 60 years anyways. Going to hot water saves a lot in the long run, but the big opportunity is when you can do heat recovery. This is showing central heat recovery. There's some things you can do on top of that I won't get into, but you can do some airside heat recovery, which is fairly easy to do with our existing systems, which just means instead of doing free cooling in the winter, and you can actually use your mechanical cooling by using chilled water to heat up that chilled water so you can then do heat recovery with it even in the winter. So basically getting a little more heat recovery out of the chilled water in the winter by not using free cooling, which sounds counterintuitive, but actually makes sense. So that's something we can do to without much additional capital costs or no additional capital costs, getting some extra operational savings. We also looked at a distributed heat recovery system where we would have heat pumps at all the buildings, maybe small districts. Looking at the chill water system as we already have this heat collection system, can we just put heat pumps on it in various places and heat buildings and not have to put the distribution system in for hot water? The challenge for us is the number of buildings and all the upgrades that would be required at the building level to meet the electrical loads for all those heat pumps and the maintenance, operation and maintenance. You can see this is operation and maintenance of all. We were talking about several hundred new heat pumps on campus that now need to be maintained, and then the capital costs go with that. So really the best option for us is central heat recovery. The question is whether we go to full electrification or not. We're making that plan right now, but it didn't stop us from taking the first step, which was start putting in the hot water system. The full electrification plan would involve getting that additional heat that we need in the winter from somewhere other than our cooling system, because we don't have any more heat to get out of it in the winter. So the options, if we're going to fully electrify, would be the best option would be a geo-exchange. So when we can't get heat out of our buildings, run that chilled water into the ground, get it up to 60 degrees and bring it back and run our heat recovery chillers off of that. So that would be geo-exchange, really low energy. There's some costs for the drilling, but that's something we'll look at. And then that can be compared to, say, an air source heat pump solution where you're just pulling heat out of the air, heating the chill water up to 60 degrees so that you can run your heat recovery chillers year round off of that. So again, there's various places you can get that low grade heat. We're going to be looking at the different ways to do that and what's the most effective way if we're going to fully electrify. But the bottom line is that hot water is for us the pathway to get to carbon neutrality because it gives us those options. So we've started, and I'm going to just to summarize kind of what I've been talking about, this hot water solution is really the lowest life cycle cost. It for us leverages that district cooling opportunity and the ability to do heat recovery. Makes the overall system now, instead of having a cooling system that has a COP of 3 or 4, and then we have a heating system that, you know, even though the plant is very efficient, above 90%, the losses on the distribution are very high. Now tying those two systems together, the overall heating and cooling system can have a COP up in the 7 range because you're using both sides of the chiller, the heat recovery chillers. So the update though is that we've now completed this whole section of campus shown in red. So the red pipelines are in the ground. There's a couple buildings left over the next month to connect to those hot water pipelines, but we're actually heating all these buildings now with hot water. We don't have the heat recovery chillers yet. That's the next step. So we're still making this hot water off of steam from our steam boilers via some heat exchangers that we actually got for almost free from Stanford after they finished their project. So we have those temporarily making our hot water, but the next project that we're working on now and we're in the preliminary design for is to put in heat recovery chillers to actually replace our oldest chillers with heat recovery chillers. So it's a avoided cost where we were going to have to spend money on new chillers anyways. But then we're going to be able to, we also need more heat load for those. So we're planning to do this, all the yellow buildings in the next district, along with the heat recovery chillers. So we'll be able to heat this entire north half of campus off of heat recovery chillers. And the goal is that starts construction next year and will finish sometime in 2025. The key to getting this done was that we broke it into districts. We don't have the money to do the whole thing. We were able to put together the funding for this basically out of avoided costs at the boiler plant and the steam systems. Instead of spending money on this system that's losing money, let's put it into something that gets us going the right direction. And then we're just having to put together costs for each of these districts as we go and get approval as we go. So the hope is that this one's done in the next couple of years, and then we're working on the next couple of pieces as well. But the goal is that the whole campus is off of steam. Just to give you a couple pictures, this is what went into the ground. These are large plastic pipe. We actually ended up going with a HDPE pipe. It's a high temperature HDPE. So it has actually like a fusion welder. It doesn't require any special welding. It's just a machine, and they can drop it right into the ground. It has valves that are direct buried. You can see some of those here, and it's getting insulated with this gilsulate. It's a white powder insulation that's just going right into the ground on top of it or around it. So that is the way that the piping is going in the ground for the hot water. And then at the building level, the heat exchangers, this is showing an existing building that had a steam heat exchanger that came out. It was getting hot water. The hydronic system in the building was being heated by steam with a large shell and tube heat exchanger. That's been replaced now with a brazed plate heat exchanger here that's taking the loop low temperature hot water, we call it, and heating the building hot water. In new buildings, we actually can run that hot water from the loop directly into the building. But in the older ones, we put a plate frame or a brazed plate heat exchanger there because of concerns about building water chemistry and problems in the building if we run new water into the building. So most or about half the buildings have a heat exchanger, and this shows a new building, our teaching and learning complex, with some new connections to the district heating and cooling. That was our first building to be directly connected to the hot water system without ever being connected to steam. And then just to wrap up, an overview slide. Here's our existing system, or before we put in hot water. You can see the thermal energy storage tank, our chiller plant that's there, and then we have another chiller plant, total of 18,000 tons of cooling. 4 boilers. Our oldest one is actually being decommissioned, so we're going to have 3 boilers. And those heat the buildings through heat exchangers. Chill water goes directly to the building systems. And then the new system that we're going to, the chill water system is basically the same, except that we're swapping out chillers for heat recovery chillers. And that can make both hot water that's useful and chill water, putting in a hot water storage tank. And as the boilers reach end of life, we're going to replace those and the hot water heat exchangers with just more heat recovery chillers. And the goal would be for full electrification, we'd have geo-exchange wells to heat the chill water when we can't get the heat out of the buildings, in addition to or in combination with air source heat pumps that can also do the same thing. So that's the ultimate goal, and that's the pathway that we're on. Any questions?
Thanks, Josh. Questions from in the room, and then online, if you're online chat, or raise your hand.
If you look at like you generate steam and then you distribute it, what percentage of the energy in the steam gets to the building versus like the water? Do you have any estimates on that? Like if you account for leakage and
so that's one of the biggest problems with the steam system is it's going at 350 degrees Fahrenheit. We're just running it at 135 psi, but it's really hot, and even with good insulation, it's hard to insulate pipes in the ground at that temperature. Our insulation, a lot of it is 50, 60, 70 years old, and so some of it's non-existent. So we estimate 30 to 50% of our energy is being lost in the distribution. So
it's actually better than I thought, to be honest.
Okay, but we're talking a couple $1 million a year. That's just heating the grass on campus, so which doesn't appreciate. So it's a pretty big loss. The plant, like I was saying, the plant's really efficient. It's got a condensing economizer and all kinds of things to get its efficiency really high. But we've got over 20 miles of pipe. That's when you got really hot temperatures, you just can't insulate it well enough to stay that. And I mean, we get about 90% of our water back. The steam, the condensate comes back. It's not like we lose a lot of it on the distribution, but the energy, a lot of it turns into condensate on the way and never makes it to the buildings. So that's one of the big disadvantages of the steam system. at this scale.
And what's your estimate on losses for the hot water?
5%. It's going to be 160 degrees max temperature, and with that insulation, very low losses. So that's one big advantage.
Yeah, I was wondering, like, for moving on to like electrification, how are you gonna be retrofitting buildings? Because right now the buildings are using 160 degrees water, right? So are the heat recovery chillers able to achieve the temperature?
Yeah, the ones we're going to put in are going to be able to. That's unfortunately that limits us to very few pieces of equipment out there that can do that at the scale we need. There may be, by the time we're doing it next year, we're hoping there's a couple other ones that might be available, but yeah, we actually, most of the buildings were designed for 180 degrees Fahrenheit heating systems. Before we did this project, we just lowered the set points, max set points to 160 or 150 and tested it over a couple of winters and found that most buildings didn't have any problem. Most of the heating systems are over designed. And the only ones where we had issues, it usually wasn't a temperature issue, it was more either a water flow or an airflow issue that could get fixed. So the good news is they can run at 160. The bad news is they probably can't run much lower than that. So new buildings we're putting in are at 140 or 150. But you know, yeah, it would be nice if we were down at 120, we could do all kinds of different equipment for the hot water, but we're going to be a little bit limited in terms of, you know, having large industrial size heat recovery chillers.
And these chillers are going to run all the way from like providing chilled water at 40 degrees to like providing hot water.
Right. Yes. Wow. That's the plan right now. Yeah.
Okay.
So one side they're making 40 degrees, the other side they're making it 160. Yeah.
Wow.
So yeah, there's definitely a penalty there in terms of that extra lift. But when you compare it to throwing away all that heat, you know, it doesn't even compare. So
Have you looked into maybe like having the chiller run and using the chiller condenser water?
like cascading.
Yeah, it's more capital cost, but
Yeah, we have looked at that, and I mean, we haven't ruled anything out. We're actually in the preliminary design for that plant right now, so we're looking at all the options. But at least preliminarily, that looks like that's not going to make as much sense for a few different reasons. But that is something that we've looked at, yeah. Especially because it opens it up to different, you know, more typical equipment.
exactly.
Yeah.
I had a few questions from online folks, but I think you answered them. One was about when you turned on the system in the red district, did you see anything unexpected in the buildings?
Well, not yet, but it's pretty early. I mean, it's been like 2 or 3 months of running the hot water system. So far so good, but I don't think it's been fully tested.
Okay, great. I think the other ones got answered. Excellent. Any last questions? Feel free to type them in quick.
Yeah, or you can reach out.
Or reach out to Josh. Yes.
I've got a lot more detail on slides that
Okay.
I can share, but not.
And your website's great too.
Yeah.
The website, the big shift.
Yeah, but yeah, do check out that website.
And
Hi, I have a quick question. This is Yuho from CEC. I know the UCOP also had, you know, carbon neutral targets through all campuses. Are there any coordination you guys are having with other UC campuses in terms of sharing lessons learned or plans, things like that?
Yeah, actually a lot of coordination, a lot of discussion. I mean, part of that UC goal was the benefit of that is that all the campuses have been talking for the last 8 years about how we're going to get there. The challenge is all the campuses are a little bit different. They're different in terms of climate. They're different in terms of systems. So not all the campuses have a steam system, and then some have different, like for example, there's some campuses with that high temperature hot water, or a lot of them don't have the full district. They have local boilers. But we have been talking, actually, Berkeley is now embarking on a similar pathway. They are getting off of steam and they're planning that transition, but they're just probably a couple of years behind where we're at. But we're sharing ideas. They're actually coming out and visiting, and there's a lot of discussion going on there. Same with some other campuses. We're definitely sharing as much as we can. And there's a lot of lessons to be learned. And we did the same thing, like I said, with Stanford, UBC Vancouver did this. And so there's been a lot of discussion among different campuses trying to learn from each other.